introduction as well.
Now we should continue our morning session, and this is a great pleasure for me to introduce the next speaker. It is Professor Boris Baeumer from University of Otago, and the topic is a higher order resolvent positive scheme for fractional derivatives on bounded domains. Please.
Thank you very much for the introduction, and welcome everybody to my midnight session. We'll see how the Milan watch goes for me. So I'm very pleased and very grateful to the organizers, one for inviting me and giving a talk here, but also to dedicating this this day to my good friend and former colleague Mark Meerschaert. I'm sure his wife Carmen will be very pleased when she hears about that. And what I'm going to talk about today is also something that kind of came out of discussions and work we did about 7, 8, maybe 9 years ago. Okay, so what we're looking at is the fractional diffusion equation on a bounded domain. So one-sided. So if you look at the negatively skewed alpha stable process and looking at the fellow equation, you would end up with an equation like this, which of course the same as the Fokker-Planck equation of the positively skewed process, one you would usually consider on the space of continuous functions and the other one on the space of measures, or L1. L1 certainly has a lot nicer properties in terms of semigroups than the space of measures. And so if you look at this equation, so alpha is always going to be between 1 and 2 for now, so that we have not just a forward jumps, but also a backward drift, a zero mean process. And if you look at, here's my reminder that I wanted to look at the movie. So if you look at how this process evolves, you will see that it is killed at the boundaries, and then at some point you're going to see just the first eigenmode after a while. Okay. So one question one might ask is, what can we say about the rate of convergence of now numerical schemes that approximate the solution that I just showed you? Of course, I showed you a numerical approximation to that. And the answer, well, is actually quite tricky, because the solution, if you look close to the left-hand side, is usually not differentiable in X. In fact, another movie. If we look at the convergence rate, now if I take just a Gr&uuml approximation for my fractional derivative and look at the order of the approximation of the Gr&uuml scheme, we know it's order 1, and then it suddenly goes down and doesn't stay order 1 and becomes an order 0.4, because what happens is that here on the left-hand side of my solution, we grow like x to the alpha minus 1, which is not 1 times differentiable anymore, and the order of the scheme goes kaput. Okay, so if you're looking at the eigenfunctions, eigenfunctions in general will have this form. It's a Mittag-Leffler function, and if alpha is 1.4, for example, then it's going to have 3 zeros in the eigenfunction that we can choose. Other ones for which u of 1 is equal to 0, so we need to scale my function such that this point here will now sit in at 1, and that will give us the eigenfunction, the dominant eigenfunction that we see. The other 5 eigenfunctions are all just the zeros of E alpha alpha. Okay, so if you want to take a look at those, we see we have 3 real eigenvalues, and then the spectrum goes off to the left in a sectorial region on this on this smallest line, but we have our 3 dominant eigenvalues, and again The problem is that my eigenfunction has the term x to the alpha minus 1 in there, which is very bad for any numerical scheme. Because usually you get higher order or the order by removing the error term and then ending up with an error term that involves a higher derivative of my function. Okay. So if you look at a finite difference formula, that's like a quadrature formula, it usually takes this form. And so I had this idea that maybe we should just look at what would happen if we just take the x to the alpha minus 1 term out. Okay, let's remove this, meaning let's just see whether we can find W, my weights, such that the numerical approximation of the derivative of x to the alpha minus 1 is exact. Okay, so what is the derivative of x to the alpha minus 1? Well, it's a delta function at 0, or on the space C01, it would just be 0. Okay, so the weights, what should they satisfy if I just want to make it basically exact for x to the alpha minus 1? They should satisfy this equation. Or, well, since I have a 0 right here, I would I can remove the first column because it just gets multiplied by 0 and remove the first row here and end up with this nice tridiagonal system for my weights. Okay. So the weights are easily computed, and if I compare them with Gr&uuml's, well, it looks surprisingly different, right? So the Gr&uuml scheme, so the nice thing is, again, they have a negative entry in W1, which will correspond to the rate out. So it corresponds to a rate matrix. This thing here is a rate matrix of a finite dimensional process. And the rate out goes the rate W1, that's negative again, and all the other ones are positive, looks like it. And but W0 is smaller, W2 is smaller compared to Gr&uuml, and then it's somehow a similar W5, W6, all of them are a little bit bigger than on the Gr&uuml scheme. Yeah, might be or something or not. So, well, all we can do is make a little experiment and see what happens. Okay, so let's do a little numerical experiment. So we go to the next movie. Okay, so this is the order of approximation of the new scheme. And it sits at 1.4, doesn't sit at 1 and jumps down to 0.4. It actually stays at 1.4. Okay, so well, that seems to work. That's a lot better than we had expected. I guess we have a conjecture. We have a scheme that might give us order 1.4. And then the question is now, how do you prove that? Well, I guess you should have to show consistency, stability, maybe something about convergence rates, and so on. So there's suddenly a whole research program that one might endeavor. Okay, so let's take a look. Okay, so if you write the scheme as a multiplier, then we just take the Laplace transform of the scheme and see whether this can potentially make any sense. Okay, so we have this is the rate matrix applied to x to the alpha minus 1. Where we have little weights at the grid points, and that should give us basically the delta function at 0 multiplied by h. Or if we solve for our scheme, then we just divide by this bracket over here, we get this expression. And now if you look here at the denominator, and if you look at this hard enough and long enough, you see that this is actually the trapezoidal rule approximation of the Laplace transform of x to the alpha minus 1. And so this will just converge towards lambda to the minus alpha. Trapezoidal rule usually converges of order h squared. But of course, x to the alpha minus 1 is not 1 times differentiable. So there the order also drops, and it drops to the order of h to the alpha. And then multiply top and bottom by lambda to the alpha. You see that this is going to be of lambda to the alpha. This is going to be a fractional derivative plus an error of h to the alpha, at least in Fourier space. And it's not a proof of anything, but we might be on the right track. Okay. So before we try to attempt now the proof of consistency in the order of convergence, maybe we should take a first look at stability first. So in order to get stability, what we want to have is that our matrix is indeed, I want to show that our matrix is indeed the only negative entries on the diagonals, and that it is a rate matrix, so therefore a rate matrix, and that it is mass preserving. So we want to show that the weights add up to 0. Okay. Well, the weights add up to 0 because all I have to do is take lambda to 0, and I see that the denominator goes to infinity, so the whole thing indeed goes to 0. The second part, that the only negative entry is W1 and everything else is positive, that turned out to be surprisingly messy and hard, and showed this to colleagues around, and I mean, it becomes quite technical very, very quickly. And well, what I showed you so far, that happened about 5 or 6 years ago, and showed this problem to colleagues. I even gave talks at math conferences. Colleagues are smart enough to, after the professor is smart enough that after a day or two, they say, okay, that goes to help basket. I'm not quite sure where it goes. You give it to graduate students. At some point, you have some pastoral care say, no, we need to move on to somewhere else. We give it to some high school students, because after all, it's a very easy problem to state. Here's a matrix equation. Okay, can you show that W1 is negative and everything, and the other W's are positive? I have some high school students who left it up, and now I have to apologize to them for ruining their youth, but I think they had some fun with it, but didn't get anywhere either. And so the problem was stuck with that was stalled for a couple of years until my colleague Matt Perry said, well, actually, if you look at the denominator, this can also be written in terms of the polylogarithm function. Yeah, I heard polylogarithm function somewhere before a little bit, but not a whole lot. And so, well, okay, it's a polylogarithm function, so what? So one intractable problem is another intractable problem, but it turns out that a whole lot is known about the polylogarithm. After all, mathematicians try to solve some Riemann hypothesis for 150 years, and it turns out that it's very closely related to the polylogarithm. So the polylogarithm, if we replace e to the lambda, you get a t to the k, is a function that is known to be analytic in the complex plane without 1 to infinity. It's a single 0, and the asymptotics going towards infinity and going towards the singularities at 1 and along the strip is quite well known. And so it turns out you only need a little bit of complex analysis and the Cauchy integral to figure out that we can actually compute Wn and get a nice estimate, and definitely see that Wn is going to be positive. If n is greater or equal to 2, of course, we can compute it for 0 and 1, and so indeed we have shown that our matrix is the way we hoped it to be, namely that on the diagonal it's negative and everything else is positive, and it adds up to 0, which is then going to give us stability in a numerical sense. All right, so next step is to figure out consistency and the convergence rate of our process. We want to show that it is conversion of order h to the alpha. Okay, so for that, we're looking at the space of alpha times differentiable functions and want to show that it converges to the alpha derivative of that. So here's the theorem that if my function is alpha plus beta times differentiable, then the scheme is going to be of order h to the beta. So in particular, if beta is equal to alpha, so if our function is at least 2 alpha times differentiable, then our scheme is going to be of order h to the alpha. Okay, if my function is just alpha times differentiable, then the scheme still converges, but we don't get a rate. How do you prove it? Well, the proof is fully based on Fourier transform arguments, and basically just take the Fourier transform of ah to the alpha minus f of alpha, and then look at what is left. On the left, you can write it in terms of a function g beta hat, and then you use some Fourier arguments to show that G beta is an L1 function, and therefore it's an L1 multiplier. And whether it's K or KH, it's going to have the same L1 norm, and there's your estimate. Okay, well, this is on L1. What we really want to have it in the soup norm, so we need to find a way to get estimates also in the soup space. And actually turns out that we can use an operational calculus that we can transfer the rate to basically anywhere. So here's the nice generalization of our L1 result that says if we have a Banach space where minus A is a generator of a bounded strongly continuous group, so say space C0, the space of continuous functions vanishing at infinity, take A to be the first derivative operator, then G and HF is this is just f of x minus nh, so it's exactly our formula. Then we have the same type of estimate. Okay, so not only do we have an estimate in L1, we have an estimate anywhere where the shift is strongly continuous, the shift semigroup. So it's in C0, it's in all the LPs, it's in all the Hölder spaces, it's in all the Sobolev spaces. It's, if you have a drift on a torus, or if you want to go to outer space, and in all kinds of settings, if you want to have the fractional power of an operator, here's the one way to approximate this. The proof is rather very simple. It just is based on an operational calculus where you can compute G beta head of IHA, that's another operator, and you can bound the norm in the same way we bound it basically by the L1 norm of G head B of beta. And since this is bounded by C, then you also get that the norm of this operator here is bounded by C as well. Okay, so we have convergence on C of R. So if my function is 2 alpha times differentiable, then my approximation is of order h to the alpha, something that we saw in our little experiment. Okay, if f is x to the alpha minus 1, then AH alpha is 0 on all the grid points, so that's not going to give us any trouble. And well, that's not quite good enough, because we also have this term x to the 2 alpha minus 1, which is not 2 alpha times differentiable, because if I take 2 alpha times derivative, I get x to the minus 1, which is bad news again. Okay, so I only get that if I take the derivative or my scheme of my first eigenfunction, I only get order h to the alpha minus 1. So not all is lost, or I don't get that my scheme approximates the fractional derivative at the right order, but maybe a backwards Euler scheme or my scheme will at least approximate the semigroup, because we might get some smoothing from the fact that from that we have a distributive operator, that we have a nice equation on the domain, that we have an analytic semigroup, and that's exactly what is happening. So more work needs to be done to get conversion rate of solution semigroups to increase the order from alpha minus 1 to alpha, and that is we want to show that we have analyticity of the semigroup on C01. Okay. Once you have analyticity, then you know that the solution not only maps your function always into the space, into the domain of A to infinity, but also then you get estimates on the fractional derivative of the semigroup itself. Okay, so we can show that our semigroup on the space C01 is analytic, and it's reasonably straightforward. You can compute the resolvent directly, and then just get the estimates out of there. Okay. The next thing that we need is, if we want to now compare semigroups, is that we need to embed our discrete grid-based model excuse me, into the space of continuous functions. Now, if I just take a straight line interpolation, what happens? I basically again introduce error that is of the order x to the alpha minus 1, because I'll do a straight line approximation of x to the alpha minus 1. And again, that would be bad news. So one way to overcome that is to, instead of straight line interpolation, do an interpolation that is exact for x to the alpha minus 1. So between two node points, you always put a piece of x to the alpha minus 1 appropriate at a step in there, and you get, again, a finite dimensional space over which you can interpolate, and where you can have then a semigroup, an approximated semigroup on that. Okay, so here's the lemma that f is alpha times differentiable. Then the projection of f to that finite dimensional space is bounded by the alpha derivative of f. So that's one ingredient that we need. And in order to use smoothing now, what we're going to show is that even though a to the alpha of pi and f doesn't converge, or a h to the alpha doesn't converge, the inverses at least converge. And for that, then a backwards Euler scheme or other schemes have a hope of converging appropriately. And so here's the lemma that says that if our function is ax to the alpha minus 1, has a term of 2 alpha minus 1, and then is something that's alpha plus 1 times differentiable, then we're going to get this estimate on the inverse of the matrices, and that is in the end what's going to give us the crucial estimates that we need to show that we indeed get higher order convergence on C01. So that the approximate semigroup, the difference between the approximate semigroup and the semigroup decays like h to the alpha. Okay, proof for here, two things or three things. Now, first, since S of t is bounded, we can just as a contraction, the difference is bounded by f and pi and f, and so we show that this is of order h to the alpha. Then we do a little bit of semigroup magic and throw things around. We can show that those two, we have two error terms, and we can estimate those. And analyticity then implies that we can estimate this bit here, a to the alpha s of r, by c over r, and then this integral, this is what gives us the log t over h to the alpha. All right, with that, I come to the end of my talk. So we developed a finite difference scheme based on approximating the fractional derivative of x alpha minus 1 exactly, and by pure chance, we stumbled across a new set of weights that seem to outperform in Gr&uuml quite nicely, that is still has all the properties of the Gr&uuml weights, namely that it generates a stochastic process. It's a Q matrix. It is mass preserving. It keeps positivity. It does everything that you hope for. But instead of order 1, it has order alpha, and it beautifully interpolates. Of course, also if alpha goes to 2, it goes towards the central difference scheme. Everything that it should. We showed that the semi-discrete approximation of order alpha on CR. So it is a nice approximation for the fractional derivative, but it's also a nice approximation to use if you want to approximate things on a bounded domain and solve the Dirichlet problem there. And you can read the details there in the upcoming volume of fractional calculus applied analysis. And with that, thank you very much.
Thank you very much. Let's thank speaker, and we have the time for questions, please.
Hi, I was hoping to talk about for boundary value problems and with Neumann boundary conditions.
Yes.
So I was hoping to if you have any work done on that aspect, and probably would talk about uniqueness and convergence if there is any work done on that aspect.
We have a couple papers, and the third paper is submitted, and my postdoc Lorenzo will talk about this tomorrow. But the issue is it's a bit more complex, I guess, because what do boundary conditions mean? What do Neumann boundary conditions mean in a alpha stable or in a non-local context? And the question boils down to, what do you do to miss a particle that wants to jump across a boundary, right? So it goes back to Feller. Basically, it's a question of where do you reinsert it in the domain if you think that a Neumann boundary condition should somehow mean that particles don't disappear but stick around. So you can either restart it at the boundary, or you can fast forward a process and basically say we wait until the process is back inside the domain and restart it there. So those are two types of different boundary conditions. One would be that the alpha minus 1 derivative is equal to 0 of Riemann type, the other one of Caputo type. And depending on that, you get one process or the other, but it's well posed, it's beautiful semigroups, and it's all well understood.
Okay, thank you. Do we have more questions?
Hi, thanks for the talk. Maybe a very quick questions regarding this last convergence that you show us of the discrete to the continuum, let's say. Have you thought about proving the same convergence under other norms? Do you think that there is some flexibility in the choice of the norm under which you can prove these convergences?
Yes. I mean, I moved to the uniform convergence because it's pretty much the hardest one that you can do. L1 convergence and so on is usually a fair bit milder, so I don't really see much of an issue there. And certainly, you know, for not on the boundary domain but on R, I mean, we showed it for anywhere where you have where the group is strongly continuous, where the shift is strongly continuous.
Okay, thanks.
Okay, thank you very much. Do you have any more questions or comments? Okay, let's thank the speaker again.